So thank you for the introduction, Jared. Thank you to his team as well for organizing a great conference. Today I'm going to talk about time series data. In particular, I'm going to talk about two packages that I'm currently working on. One I'm currently working on, nearly submitted, and then the second you can download from R. The first one's joint work with EU from the University of Cambridge, and the second one is with my student Nadia Frolova from the University of Alberta. So time series, okay? So assuming that we have, say, I'm going to pick a simple example first. So assuming that we've, say, 8 time series data over time, if we want to measure the dependence, we could simply calculate or estimate the correlation matrix, okay? Alternatively, we could also estimate the precision matrix, which is just the inverse of the covariance matrix. If we have each time series as a node, if we label each as a node, we could also represent the dependence as a undirected graph as follows, where the edges in black represent positive partial correlation and the edges in red represent negative partial correlation. So this is an undirected graph. All these previous methods are what we call static representations of dependence. So we're just looking at, over the whole time course, what is dependence between each of these time series. They do not consider the fact that there's probably changing correlation between the time series over time. Okay? So today, in the past few years, there's been recent interest in looking at this, what we call time-varying dependence or time-varying undirected graphs. So the previous methods that we looked at, so the correlation, covariance, and precision matrix, all have natural time-varying analogs. So if we have these precision correlation in conjunction with a sliding window, this is one measure of estimating time-varying dependence. So for example, if you have several time series, one way is for measuring time-varying dependence is you specify a sliding window, say of length 100 time points, and then you can estimate the covariance, correlation, or precision matrix for that window. Okay? Then you can simply shift the window in time. You can have overlapping or non-overlapping windows and do the same thing, estimate the covariance, correlation, or precision matrix. Okay? So this is a nice, simple way for estimating time-varying dependence. Okay? However, there is some limitations of this technique. Okay? Obviously, the length of the window is very important for estimating this. Okay? And also, when you're estimating the correlation, you can also have a weighted average of the previous data points. So how much weight you should put on the previous data points is also critical. So today, I'm going to introduce a new method that for estimating time-varying dependence that doesn't make use of a sliding window. Okay? And the method is based on or inspired by the community detection in an undirected graph or undirected graphs. So here we're looking for closely knit or tightly knit communities of time series that are loosely connected to other clusters as well. So again, if we have a simple example, so if we have 8 time series and each time series is represented by a node, we're interested in finding communities or clusters that are closely knitted together, and then the communities are loosely linked to one another. So I only have 20 minutes, so I have to do 2 packages, so I'm going to be quite brief. Okay? For more interest, there's a paper and there's also a package. But what we do is we consider a data-driven technique, which we call network change point detection. And what it does is it estimates change points in the community network structure, where we don't know where the change points occur, and we don't know how many change points there are. The method is a 2-step technique. So in the first step, we estimate where the change points in the network structure are occurring. And then after performing some inference, we estimate the network structure between each pair of significant change points. Okay? And then we assume that the network structure remains constant between each pair of significant change points. So graphically, what does this look like? So assume that we have a number of time series. One of the upsides of this technique by considering communities is we can consider a a number of time series which is greater than the number of time points. Okay? So assume that you have, say, a number of time series which are each represented by a node. So you can see here that there is 2 communities for the first 100 time points. Then the membership of each community changes in the second 100 time points, and the number of community changes to 3. And then in the last 100 time points, again, the membership for each of the time series in each of the communities changes again. Okay? So this is, you can somewhat see this as the truth. What our method does is it estimates where the change points are occurring, so we'll estimate row and new, and then after carrying out some inference, we'll then estimate the community network structure between each pair of significant change points. Okay? So that's the method, the algorithm, etc., description, all in the paper. So I'm just going to have to refer you to that. We're going to apply this to a high-dimensional time series from a functional magnetic resonance imaging experiment. Okay? I'm not sure whether someone spoke on this yesterday, but most of you have probably heard of MRI scan, where you're looking for the structure of your brain. Okay? So is the structure of your brain intact? Okay? So when you go into an MRI, that's normally what they'll put you into, an MRI scanner. An fMRI scanner is they're looking how your brain functions over time. Okay? So it's a specialized MRI scan. It's non-invasive. Okay? And during the course of this experiment, so as you're solving some maths puzzle, or you're being burnt in some cases, or you're simply just resting, we take a series of brain images while you're doing these tasks. Okay? And so what happens is, you can imagine the brain as a large cube, and then this is divided into smaller cubes, which we call voxels, and within each of these voxels, we get a signal. Okay? So you can think of, we get a signal, and then within each of these voxels, we get a signal over time. Okay? So you can think of this as a high-dimensional time series problem. So what we do is we take various regions of your brain, and from each of these regions, we get a time series. Okay? So what are we interested in? Well, we're interested in how the connectivity within your brain changes over time, changes as you're performing a set of tasks. Okay? So people are beginning to look at this. People started off just using static representations, but now people are looking at more dynamic representations of your brain activity. So this has been linked to various brain disorders such as Alzheimer's, schizophrenia, etc. So the experiment that we have is just on controls. So we have 285 time points. So we have 285 scans of your brain. And we consider just 116 time series. Okay? So it's not one of these high-dimensional cases where the number of time series is greater than the number of time points. So we apply this to 45 subjects, and what I'm showing you here is just the significant change points for each subject. Okay? And this is a resting state experiment. Okay? So for those of you who don't know what a resting state is, you're simply, well, a graduate student is simply put into the scanner and told to rest. Okay? Now, obviously, it's quite hard just to rest and think of nothing. Okay? So even when people are at rest, their states, their functional states, are changing over time. And this is what we find. Okay? So some subjects have 4 change points, some subjects have 2, some subjects have 4, and you can see 16 has none. What happened to 16? Fell asleep, probably. Okay? Or meditating is another example. So I'm just going to focus in on 3 different subjects here. So we've subject 1, 3, and 15, okay? And we have then the community network structure for different regions in the brain, where the regions are represented by the nodes, and then the communities are represented by the colors, okay? So this is great. So we can see that there's changing functional connectivity or connectivity within the brain or time-varying dependence over the experiment. But what we would like to do is see if different states are similar across subjects, okay? So if they put me in the scanner and I've had an easy day, maybe I reach the default mode network, what it's called, pretty quickly. But maybe someone else is sitting there and they're thinking about different things, their exam the next day, and they don't reach this functional state till partition 3. So what we want to see is, for controls, and in particular for patients with brain disorders, is there common functional states across subjects, okay? So I didn't talk about it earlier, but the metric that we use to find the change points is we look at the rotation of the subspaces, okay? Or in particular, the cosine of the principal angles between two subspaces. This is the metric that we use to find the change points. This method also allows us to find common functional states across subjects. By doing the same calculations for graphs between two different subjects, will also give us a metric about how close they are to one another, okay? So, for example, I'm just going to show you a few examples. This is subject 2 partition 2. This is subject 20 partition 2. So these two states are similar. So if you look at the cluster of nodes that are similar, so you can see that the yellow nodes here are similar to the yellow nodes here, and then the pink and aqua are similar to the aqua and pink on this side. This is subject 1 partition 2 and subject 4 partition 3. So you can see again that the yellow nodes in D are similar to the aqua nodes in C, and the pink nodes in C are similar to the pink nodes in D. So these, we can say, are similar functional states across two different subjects. So again, these are just for controls, okay? Ideally, we would like to also see what happens if we had controls on people with brain disorders. Is there common differences between the control groups and the patients, and what are similar across the two groups and different? And then hopefully by using our method, which is novel in that we can allow for a large number of time series, that this can lead to better diagnostic and prognostic indicators for these disorders. Okay, so the package for this method is available to download locally. We're having a bit of trouble with the R people. So the average time to run the algorithm on a data set with 285 time points on 116 time series is about 2 minutes on my laptop. So it is quite computational. Obviously, more cores, more nodes, this will improve. So if you're interested, please download this. Okay, so I wanted to give you a break because I'm going to change it up now. So I'm going to show you a nice slide of my favorite flag of a former state. Does anybody know what the state is? The former flag of a nation. Anybody?
Lebanon?
Yes. No, not Lebanon. Close. Libya. Yes. Who said it? Yes. The former flag of Libya, all green. Okay? So that's my change-up. Okay. Extreme events. I told you, it's a bit of a change-up, okay? So we're going from brain imaging to finance, okay? So recently there's been some interest in trying to understand extreme events, okay? So this can be applicable to climate and also to finance. So extreme events are rare and they occur in both of the tails of the distribution. So we're only interested in what's happening in the tails. So they're rare, so they occur infrequently. So people have done a lot of work on trying to understand extreme events. So this is very interesting on its own, okay? But what we're interested today is the dependence between extreme events, okay? So this temporal dependence can be within one time series, or probably what's more interesting in the extremal dependence across time series, okay? So given there's an extreme event in one time series, what's the probability there's an extreme event in another time series in the future? So we're going to consider a new statistical methodology called the Extremogram. So it's kind of like the parallelogram or the autocorrelation function. So it's the extreme value analog of the ACF, okay? So the ACF looks for linear dependence of the center of the distribution. The extremogram only considers events that are occurring in the tails of the distribution, okay? So in simple terms, it computes the extent to which a large value of a time series has on a future value of the same time series or another time series, h lags ahead. So the data the extremogram considers are extremes, so they're rare, so we need large sample sizes, okay? This is great because in finance, we have a large number of time points, okay? So the extremogram and its derivatives can easily describe graphically and quantitatively the size and persistence of the extreme value clusters. So here's what the extremogram looks like. So it's like a conditional probability. So given that I've extreme value now, what's the probability that I have an extreme value h time lags in the future? So it's simply just an indicator function where we just line up the two time series, one the original time series and the other lagged time series, and we look at whether there's an extreme event in both of these time series, okay? Now you may ask, well, what's an extreme event for a time series? Well, it's whatever you want it to be. So if you think an extreme event is in the less than a 1 percentile, or if you're interested in the upper tail, an extreme event is in the 98th percentile, that's up to you. Okay, so you can do it for both lower tail and upper tail events. So what are we interested in? Well, we're going to study we're going to use the extremogram to study the persistence of extreme price outcomes in electricity markets. So you may ask, well, why did he pick electricity markets? Well, I have a collaborator who works in electricity markets and has access to this data, okay? So we're interested in the persistence of half-hourly spot electricity prices for 5 regional markets in Australia. And we're interested in not only the extreme events within the time series, but we're interested in the extreme events across the 2 different regions, okay? The regions are allowed trade with one another. So our study yields important insights into extreme spot electricity prices, the persistence of these, the spillover effects from one region to the other, and the impact of these interconnectors between each of these regions. So this is what the extremogram looks like. Again, you should think about it as the extreme value analog of the ACF. Okay, so the ACF, we're just looking at the dependence within the center of the distribution. Here we're looking at the dependence in the extremes. So here you can see this is for South Australia, New South Wales, Queensland, and Tasmania. These are all regions within Australia. Was there an Australian person here?
There was.
Okay, so this is for the one person here. So here you can see that there's persistence in the extreme value. So this first lag here is, given there's an extreme value now, what's the probability there's an extreme lag half an hour in the future? Okay, so you can see that there's some persistence here. You may ask, well, why is there some spikes or significance around lag 48? Well, this is, given that there's an extreme value now, what's the probability there's an extreme value 1 day ahead? Same time, 1 day ahead, half-hourly spot electricity prices. So again, depending on which region you're in, the representation is slightly different. In the interest of time, I'm going to move on to probably what's more interesting is cross-extremograms. So given that there's an extreme value in one region, what's the probability there's an extreme value in another region? So I've kindly added a nice plot of Australia here for you to see the relationship between them all. So this is conditioning on New South Wales. So this is conditioning on New South Wales. So given that there's an extreme value, so again, I think I'm looking at upper quantile extreme value. So given that there's an extreme value in New South Wales, what's the probability that there's an extreme value in A is Queensland, which is just north of it, B is South Australia, C is Tasmania, and D is Victoria. So you can see that there's a lot of persistence between New South Wales and Queensland because there's a connector between these two. They can trade off one another. Between Queensland and Tasmania, between New South Wales and Tasmania, you can see that there's no extreme value what happens in this market in Tasmania is not affected by prices in New South Wales because there's no interconnector between these two regions. Okay? You may ask, what are these little confidence bands? So if they're outside, these are empirical confidence bands based on the permutation procedure. So if they're outside this, they're deemed significant. So why is this important, or who might this be important to? This is important for risk management and hedging decisions. And hopefully, if there's people here, people like large producers, retailers, and merchant interconnectors, if they're interested, they should apply these extremograms to the data that they have to help with these decisions. This red light is flashing at me, so I'll skip on these two slides. One is the trivariate extremogram, so for 3 series, and we've got 4 series, 5 series, etc. There's a package called the Extremogram. This was made by my student, Nadia Frolova, so if you have any questions, I recommend that you contact her, okay? And here are some references. Thank you very much for your time.